Welcome to this video on kinetic and gravitational potential energy. We will explore how energy is stored and transferred in objects that are moving or elevated. In this video, we will cover 4 key areas: the definition and calculation of kinetic energy, the concept of gravitational potential energy, how these energies are transferred, and essential exam tips. Kinetic energy is the energy an object has due to its motion. Whether it is a sprinting athlete or a moving vehicle, the faster and more massive an object is, the more kinetic energy it possesses. Kinetic energy depends on both mass and speed. While increasing mass increases kinetic energy, speed has a much more dramatic effect because it is squared in the calculation. The kinetic energy equation is E equals 1/2 times mass times speed squared. Memorizing this formula is crucial for success on your physics papers. Units are vital in physics. Ensure energy is in joules, mass is in kilograms, and speed is in meters per second before starting your calculations. For a car with a mass of 1,200 kilograms traveling at 20 meters per second, we apply the formula to find the kinetic energy is 240,000 joules. Remember that since speed is squared, doubling your speed quadruples your kinetic energy. Tripling the speed increases energy by a factor of 9. In exams, always explicitly state that speed is squared when explaining changes in kinetic energy to ensure you receive full marks. Gravitational potential energy, or GPE, is the energy an object stores due to its vertical position above the ground. Lifting an object stores this energy. GPE depends on mass, the gravitational field strength of the planet, and the height of the object. On Earth, the gravity value is approximately 9.8 newtons per kilogram. The formula for GPE is mass times gravitational field strength times height. Unlike kinetic energy, this is a linear relationship, meaning doubling any variable doubles the total GPE. Gravitational field strength varies by location. While it is 9.8 newtons per kilogram on Earth, it is lower on the Moon, affecting how much GPE an object stores. Lifting a 5-kilogram box 3 meters high on Earth results in a GPE gain of 147 joules. This energy is transferred and can be converted back to kinetic energy when the box falls. Finally, remember your units: energy in joules, mass in kilograms, gravity in newtons per kilogram, and height in meters. Always use the vertical distance for height. When you lift an object, you are doing work against gravity. This energy comes from your chemical energy store and is transferred to the object's gravitational potential energy store. This energy transfer illustrates the law of conservation of energy. The work done against gravity equals the gravitational potential energy gained, and no energy is created or destroyed. When an object falls, gravitational potential energy is transferred into kinetic energy. As height decreases, the object speeds up until it potentially hits the ground. During a fall, the total mechanical energy remains constant if we ignore air resistance. The energy shifts from potential to kinetic as the object descends. In free fall, the energy lost as gravitational potential energy equals the energy gained as kinetic energy. This allows us to calculate an object's speed from its starting height. A roller coaster provides a classic example of this transfer. At the top of the hill, the car has maximum potential energy, which converts to kinetic energy as it descends. Let's look at an example. A 0.5 kilogram ball dropped from 10 meters will reach a speed of 14 meters per second just before impact, showing how we can equate GPE and kinetic energy. Remember, kinetic energy depends on mass and the square of the speed, while gravitational potential energy depends on mass, gravity, and the vertical height. Comparing these equations is fundamental to solving problems where energy is transferred between different stores, a core requirement for physics examinations. Avoid common errors. Always square the speed, use vertical height, ensure correct unit conversions, and show your step-by-step working to secure method marks. A pendulum shows energy cycling between potential and kinetic. At the peak, energy is purely potential. At the lowest point, it is fully kinetic. When a ball bounces, energy transfers repeatedly. With each impact, some kinetic energy is lost to thermal and sound stores, causing the bounce height to decrease. If you need to rearrange the kinetic energy formula to find mass or speed, remember that speed requires a final square root step to isolate the variable correctly. Similarly, to find mass or height from GPE, simply divide the energy value by the known constants. Consistency with units is key here. Finally, always follow a structured approach. State the formula, show your substitutions with units, and provide your final answer with the correct unit, which is joules for energy. Let's do a quick recall quiz. Can you define kinetic energy, explain gravitational potential energy, and write down the formulas for both? Also, recall the standard value for gravitational field strength on Earth. Reviewing key vocabulary is essential. Remember that kinetic energy is the energy of motion, while GPE relates to position. Gravitational field strength on Earth is roughly 9.8 newtons per kilogram, and remember that energy is always conserved. These concepts have many real-world applications, from hydroelectric power stations using falling water to wind turbines and roller coasters. Our world is constantly moving energy between kinetic and potential stores. Keep this formula card handy for your revision. Remember, in the kinetic energy equation, speed is squared. For GPE, use 9.8 for gravity on Earth. And remember that these conservation laws assume no energy is lost. To wrap up, remember these key takeaways. Speed is squared for KE, G is 9.8 on Earth, energy is conserved during free fall, and always double check that your energy units are in joules.